I am Professor J. N. Mandal, Department of Civil Engineering, IIT Bombay. Now, we will perform the puncture resistance test. This as per the specification ASTM D6241 and ISO 12236. Main objective of the test to determine the puncture resistance of a geosynthetic material. This test method can simulate the stresses in the geosynthetics when a rock falls on it. For example, that this is the kind of the aggregate or this is the another kind of the aggregate material. So, this is the aggregate and this also the aggregate. So, geosynthetic material is like this. This is the geosynthetic material is placed. So, this is geotextile. Now, this aggregate is pushed upward. This is the aggregate. This pushed upward. So, that means this geotextile material is pushing upward direction and this is the aggregate which is drop downward. So, this aggregate dropped downward. So, when it is this aggregate is dropped downward, this aggregate is dropped downward and this one may be the angular very sharp kind of the aggregate, the other may be flat type of the aggregate which the aggregate drop in the downward direction. Now, these two situations can be simulated with the laboratory. Suppose this is the field situation and this can be simulated with the laboratory test. So, one may be the static test, another may be the dynamic test. So, this is the Cbr Plunger Test. Okay. This we call the Cbr plunger test, or this can say static case. This is the static case. This here Cbr plunger, and geotextile material is clamped here. This is the geotextile material. Geotextile material is clamped in a Cbr mold, and then air to plunger, a load is applied to the plunger here. So, this is called the plunger. This is plunger. So, you apply the load through the plunger on the geotextile, and you can measure what will be the puncture resistance of the geosynthetic material, and this is in case of static case. In dynamic case, or what you call the drop contest. So, for example, this is the modified Cbr, and geotextile material is tightened to the clamp here. So, this is the geotextile, and you have to place a plunger, solid cone. This is like a solid cone. This is a solid cone. Solid cone. This solid cone is to be dropped from a particular height, and it has also the weight. So, this we call the drop cone test, and this we call the dynamic case. Dynamic case, because you are dumping this solid comb at a particular height on the top of the geotextile material, and geotextile material will plunge, and then you can determine that what will be the diameter of the geotextile material due to the plunging. And to simulate the field conditions, suppose it is a very soft clay. So, in the laboratory sometimes you can use some water here, okay, to simulate the field condition. So, what we discussed, Cbr plunger test, that is one in the static case, and the another is the drop cone test, which we call the dynamic test. Now, geotextile may puncture due to the presence of a sharp stone or the root during the backfilling of the soil and compaction by the roller and or the traffic load. So, for example, that this is the situation okay. And this is the geotextile material. Geotextile material. And this distance is, let us say, the d of A, and this is the T vertical. And this distance from here to here is d of H is equal to d of A. And this is the PG, P of G, or you can say this is the also P of G, P of G. So geotextile may puncture due to the presence of any sharp or the stone or root during the backfilling of soil, compaction by roller or the traffic load. So what is the vertical force exerted on the geotextile that we want to determine? So what will be the vertical? Vertical forces exerted on the geotextile. Exerted on geotextile. So this T vertical, we can write the equation that T of vertical is equal to pi into dA into dH into P of G into S of dash. So where dA is equal to where d of A is equal to average diameter, average of the puncturing objects. Puncturing object. And dH is called protrusion height, which is equal to d of A. That means here you can see dH is equal to dA. This is protrusion height, and this is the dA is equal to average diameter of the puncturing object. And Pg is the pressure on geotextile from tire. So, here is the PG pressure on the tire, and S dash is the shape factor, and this is equal to 1 minus S, and S is the sphericity of the object, sphericity of the object. So, this is the equation you can use for the vertical pressure. Now, this vertical pressure or force can be converted into the tensile forces. Can say now the vertical force can be converted into tensile force of the geotextile. So, then we can write this equation T of vertical divided by T of required is equal to d of A divided by d of I, or I say T required is required tensile strength of the geotextile. And d of I is the apparent opening size of the geotextile. Di is the apparent opening size of the geotextile, and dA average diameter of the puncturing object. So, then we can write the equation, hence we can write T required is equal to T of vertical this divided by dA upon d of I. That means this will be equal to pi into dA into Pg into S dash divided by d of A into d of I. So, this we can write pi into dA into Pg into S dash into d of I. So, this is the equation for what is the T required. So, what we require for T. So, what are the equipment and the accessory required for this test. So, you need the testing machine and plunger with a flat of 50 millimeter, you can see here, diameter, and clamping apparatus with internal diameter of 150 millimeter. So, this is the puncture resistance test apparatus, and all the apparatus have been indigenously developed in IIT Bombay. Now, what is the procedure for performing the test? So, you have to select the load range of testing machine such that rupture occur at 10 to 90% of full scale load. Center and secure the test specimen in clamping apparatus. Test at the machine speed of 50 millimeter per minute until the specimen rupture completely. The maximum force is recorded as puncture resistance. The average puncture strength is calculated and is reported as puncture strength of the geosynthesis material. You are to perform 5-6 sample and then you take the average and determine what should be the puncture strength of the geosynthetic material. So, from this also you can make that design chart for the required puncture resistance due to the application of the pressure of geotextile material and what should be the pressure at the geotextile stone interface. So, here I am showing you that this is the pressure geotextile stone interface in kilopascal. So, defined pressure 50, 150, 250, 350, 450, 550, 650, 750, 850, 950 and 1050. And y axis is the required puncture resistance and with a factor of safety is 2.5. And di I mentioned this is 4.40 millimeter, shape factor S dash is equal to 0.24, and these are the different diameter of the stone. Suppose if you use 15 millimeter diameter stone, 30 millimeter diameter, 60 millimeter diameter, 90 millimeter diameter, 125 millimeter diameter stone, 150 millimeter diameter stone, 200 millimeter diameter stone or 300 millimeter diameter stone. So, knowing the pressure or the puncture resistance of the geotextile material for a particular diameter, then you can determine what will be the pressure on the geotextile stone base interface. So, whatever the type of the different diameter of the stone material is available on the site. So, accordingly knowing that what will be the pressure at the geotextile stone interface and what will be the required puncture resistance, that also you can find out from this diagram. Okay. Now, I will say about the recommended sum factor used in puncture analysis, which is dimensionless. So, you can say this is the puncturing object, and defined value of S1, S2 and the S3. This is recommended value for factor used in the puncture analysis, which is dimensionless. So, for example, if it is a angular and relatively large, so S1 value is 0.9, S2 value is 0.8, S3 value is 0.9. Okay. If it is a angular and relatively small, so S1 value is 0.6, S2 value is 0.6, S3 value is 0.7. Third, if it is a sub-rounded and relatively large, then this S1 value is 0.7, S2 value is 0.6 and S3 value is 0.6. If it is sub-rounded and relatively small, then S1 value is 0.4, S2 value is 0.4, S3 value is 0.5. And if it is rounded and relatively large, then S1 value is 0.5, S2 value is 0.4, S3 value is 0.3. And if it is a rounded and relatively small, then S1 value is 0.2, S2 value is 0.2 and S3 value is 0.3. So, here that S1 is called the protrusion factor and S2 is the scale factor. And S3 is the shape factor. So, depending upon the type of puncturing objective, so you have to take in the equation that what should be the S1 value, S2 value and S3. You know, if it is angular and relatively large, or it is angular or relatively small, or it is a sub-rounded or relatively large, sub-rounded or relatively small, or rounded or relatively large, or rounded or relatively small. So, depending upon the various type of the puncturing objective, you can take this value that S1, S2, S3, S3 and then you can solve the problem. Thank you.